All right, so this is homework number 13. This is the back side. I accidentally got a little carried away and I already did this problem, I think, in the notes part, but here were the answers to that question. This type of graph is a phase diagram, and it gets really confusing because, like, so this is a phase diagram and they look like this, right? And then we've got heating curves, which don't even have any curves on them at all. Like, these are heating curves, but they're straight lines. And then the new one for today is a vapor pressure curve, which thankfully does have some curves, but try and keep these straight. The names don't necessarily matter. You don't have to know, oh, a phase diagram looks like this. What I do when I analyze a graph, especially if it's one I'm unfamiliar with, I'm not super familiar with these graphs. Like, obviously I'm the teacher, but I didn't see these in my classes. So let me go through the following as if I were like a student seeing these for the first time. So zoom in. I'm gonna look, see if there's anything that I can just deduce. On the bottom, I've got temperature, which is great. I know what that is, degrees Celsius, cool. Vapor pressure, okay, measured in kPa. Pressure is something that's exerted from gases. Gases have pressure. Vapor pressure must be the pressure that's caused when the liquid turns into a gas, because the liquid, when it's in liquid state, the liquid in the cup is not exerting pressure. But once the liquid becomes a gas, now this gas has pressure. So the vapor pressure is the pressure that's coming off of a substance that is evaporating. Okay, so I've got temperature and vapor pressure, and kPa. Honestly, in high school, I wouldn't know what that is. Probably first years of college, I wouldn't either. I just go, okay, well, kPa, apparently that's how we're measuring vapor pressure, but just so you're aware. Sometimes pressure is measured in pascals, and this is a kilopascal. I don't really like it, but that's what it is. So, okay, cool. So looking at the graph, it looks like I have 3 different substances that I'm comparing. I have water, that looks like CCl4, and CHCl3. So those are my 3 substances, and they each have a curve. Okay. Now, number 3A is a definition question. If you didn't know what the word volatile meant, you wouldn't be able to answer this. So this is one that you're going to want to know. If someone is a volatile person, I would say that means they're like likely to like go off the rails, or they could like explode at any time. They're really fragile, whatever. So volatile in a liquid is saying that at any point it has just this high tendency to like it's going to evaporate very quickly. So let's see. Volatile. If it's a volatile liquid, it means it vaporizes slash, another word for that would be evaporates slash boils, whatever you want to do, very easily. If it boils easily, you could say that its boiling point is low. we don't have to achieve a high temperature in order for this to boil. So which substance in the graph is the most volatile? Okay, cool. So I just need to look and say, I'm looking for the point, the lowest boiling point. So on the one axis here, I've kind of got temperature, and the other I have pressure. So if I'm looking at this, I'm going to say that CHCl3 has the lowest boiling point. The reason that is because no matter what temperature I'm looking at, like if I was looking at just this line that they've already drawn for me, CHCl3 is crossing it first. If I follow it down, 60 versus 75 versus 100. I know that the boiling point of water is 100, and this is matching up perfectly with that graph there. So the lowest boiling point, CHCl3, is at like 60. Cool. The vapor pressure of CHCl3 at 50. Okay, so here's 50. And I'm trying to follow it up until the intersection with that. And the associated vapor pressure is 70 kPa, even if you forgot what those are, kilopascals. What is the normal boiling point of CCl4? And you're thinking, now hold on a second, you told me that normal was at 1 atmosphere, and this isn't even in atmospheres, it's in pascals. Ugh. But because this graph has water on it, it's very useful, because water at 1 atmosphere boils at 100 degrees. So check it out, 100 degrees meets right there. So I'm thinking there's something special about this line that they gave us. I'm going to make the bold assumption that 101.3 kilopascals is equal to 1 atmosphere, simply because I know that water has a boiling point of 100 at 1, and that's right on that dot. So the normal boiling point of CCl4 would just be, where do we cross for this guy? And I would say about 75 degrees Celsius. What is the boiling point of water if the pressure is 30 kPa? Okay, so here's 30. Bam, there's my intersection. About, what is that? 70. Did I do that right? 30 kPa. 30 to water. Okay. So what this is saying is, even though it seems a little bit strange, you can apparently get water to boil at 70 degrees if your pressure is only 30 kPas. So we'd have to crank sea level and really reduce the pressure to get it to do that. What is the general trend for vapor pressure as temperature increases? So as my temperature is going up and up and up and up this way, my vapor pressure, what is it doing? Well, the higher the temperature, the more energy is available to convert the liquid to the gas state. So it makes sense that our pressures are also going up, up, up. What is the relationship between IMFs and vapor pressure? Well, the more IMFs you have, the more sticking together that you'll have. The more sticking together you have, the more likely you are to be a liquid. So oppositely, if you had less IMFs, you'd have less sticking, you'd be more likely to be a gas, and gases are the ones that exert that vapor pressure. So here's what I wrote for my actual answers here. Don't mind my little scribbles. Oops. So the more IMFs there are sticking the molecules to each other, the less likely they are to evaporate. And I should have added another sentence. The less likely they are to evaporate, the less vapor pressure there is. I should have added that sentence. Please add it when you write your answers. And the last one, number 4, at sea level, atmospheric pressure is 1 atmosphere. That makes sense. Denver, Colorado is known as the Mile High City, meaning it is a mile above sea level. Would you expect the atmospheric pressure in Denver to be higher or lower than 1? So the way that atmospheric pressure works is like, here's the Earth, at least half of it. There's like all the land that we're on. And we have our atmosphere around us. Even though the atmosphere is, gas, it still weighs something. And if you're here, you're feeling all of these gas molecules pushing down on you. If you're at sea level, we call this 1 atmosphere. Now, let's say instead of being on the sea level with the sea, you're on top of a mountain. You're up here. Boop. So you have a lot less gas particles pushing down on your head due to gravity. So if this is Denver up here on a mountain, they're going to have less atmospheric pressure. Simply because they're higher up, so they've got less particles between space and them pushing. So there's less pressure, that's the point. So if there's less pressure, do we expect a pot of water in Denver to boil at 100 degrees or higher than 100 degrees or less than 100 degrees? So, my answer here. It actually turns out that it's about 95 degrees, and you'd have to explain why. When external pressure, when the pressure outside of the pot, just the regular pressure, is equal to the pressure of the vapor pushing up, that's when it boils. Since Denver has less pressure on the outside, less external pressure, we're going to boil at a lesser temperature. If we went to Mount Everest, which is even higher than Denver, we'd have even less pressure. And so our vapor wouldn't have to push as hard, and we could boil at an even lower temperature. I kind of want to Google this now. Okay, somebody pause the video and figure, not that you can tell me, but I want to know what temperature water would boil at on Mount Everest. So part C is an extension of that. Will it take more or less time for the water to boil? And if we're only heating it up to 95 degrees, well, that's going to take less time because less energy. Many families use pressure cookers like an Instant Pot in order to speed up the time it takes to cook food. Explain how a pressure cooker is able to do this in terms of pressure and boiling point. So the way your Instant Pot works is that it puts a ton of pressure inside of the container. The higher the pressure, the higher temperature the food can get without boiling. So that's how it works. It's just manipulating, like, we don't want the food to boil. So we're going to crank up the pressure and we're going to make it so we can actually cook the food at hotter temperatures where it normally would be boiling, except for that it's not. And so that's going to help our food cook faster.